Hello everyone and welcome to section 3.4. In this lesson we're graphing a system of inequalities, so it kind of ties in a variety of different lessons. Earlier this year we graphed inequalities where we had to shade and use a dotted line and a solid line for different things and so on and so forth. So that's going to come into play. We've also graphed a system of equations, meaning two or more equations, so we're going to be doing that in this lesson as well. So it's kind of a combination of a few different things. So for this one, let's graph the inequalities. So when we graph inequalities, we need to remember that when it's greater than or equal to, we shade above the line. When it's less than or equal to, we shade below the line. When it's greater than or less than, we use a dotted line. When it's greater than or equal to or less than or equal to, we use a solid line. I believe everything in this lesson is greater than or equal to or less than or equal to. As you can see, they're always greater than or equal to or less than or equal to. So we don't need to worry about dotted lines, but just if it ever comes up on an assignment or on a test, make sure you know that if it is greater than or less than, that you use a dotted line. But for all these ones, it's greater than or equal to or less than or equal to. With that being said, let's now put all of these into slope-intercept form. So changing this down here, I would subtract an x to make a negative y is greater than or equal to a negative x plus 2, because I'd have to subtract the x over. And then I'm going to divide by a negative 1 to get y all by itself. So y is now, when you divide by a negative, you need to change the sign. Hopefully you remember that. So now it's less than or equal to a positive x minus 2. So this is one equation that we are going to graph. Why don't we just do that right now? So the y-intercept is a negative 2, and our slope is 1. So up 1 over 1. And then we connect these with a straight line. With a solid line, sorry. So there's my first one. Now let's talk about the shading on this one. It is less than or equal to. When it's less than or equal to, I shade everything below the line. So it's all of that. So now let's graph this one. So let's again solve for y. So I'm first going to subtract an x. So now we have 2y is greater than or equal to a negative x plus 2. Divide both sides by 2. Y is greater than or equal to a negative 1/2 x plus 1. So let's graph this one. It has a y-intercept of 1. And then what we have is we have a slope of a negative 1/2, so down 1 over 2. And there's your slope. So let's connect these dots with a solid line. And now let's shade on this one. So when it is greater than, we're going to shade everything above the line. So let's shade everything right up in here. So now what we have here, class, is we have a system of equations, and what our solution is a wide variety of points. In fact, it's an infinite number of points where the two shadings come together. So the common part of both shadings, where the red and the green are, this is going to be our solution. So what I want you to do is, just the way I've done it up here, is graph those two different spots, and then the common area where the two colors overlap, I want you to make that very, very, very dark. That way you're telling me very, very clearly, this is my solution. All of these points satisfy both equations, so this is my answer. That's what I expect from you on your next chapter test. So now that I've done problem number 1, why don't you guys try problem number 2? Pause the video, please. Work on number 2. So hopefully you got this. Changing this one into slope-intercept form. A negative 2y is less than or equal to a negative 3x minus 4. Divide both sides by a negative 2, so y is now greater than or equal to a positive 3/2 x plus 2. So a y-intercept of 2 and a slope of 3/2. So up 3 over 2 That would be the same as left 2 down 3, left 2 down 3, left 2 down 3. So we have a graph that looks like, or a line that looks like this. And this is greater than or equal to, so I'm going to shade everything above the line. There we have for that one. So now for our next graph, we got 4y is greater than or equal to a negative x minus 12. Let's get y all by itself by dividing both sides by 4. So y is greater than or equal to a negative 1/4 x minus 3. So graphing this one, you have a y-intercept of a negative 3. And then your slope is down 1, right 4, which is the same thing as left 4, up 1. So there's our graph for the second equation, the line rather. And this one you are going to shade everything above the line because it's greater than or equal to. So we have both of these, and the common shading where both of them exist, where the green and the red exist together, that's going to be our solution. That's what I wanted you to make extremely, extremely dark. So make sure that you let me know what your answer is with no doubt in either of our minds as far as what you shaded. I think we can all agree that we know that our solution is in that top left-hand corner of our graph where the black shading is. So make that as obvious on your paper as it is on mine. So that's what I expect from you on your next chapter test. Now we're going to add in one more thing to the mix. It says once we find the shaded area and vertices, we want to find the maximum, minimum values for a function of x, y as being this. It might sound kind of confusing right now, but all we want to do is we want to get a shaded region and find the vertices where that shaded region occurs. So we're going to do the exact same thing we did on problem number 1 and 2, and we're going to do it for problem number 3. Okay, so let's do this. X is greater than or equal to 1. So that's going to be a vertical line at 1. And we have this. Right? And now it says x is greater than or equal to it, which means it's everything to the right of 1. It's bigger than 1. So this is our first answer, or for our first equation. Our next one is y is greater than or equal to 0. So if y is greater than or equal to 0, that's a horizontal line, and it's at 0. So it looks like that. And now it's everything that's greater than or equal to it, so that means it's shading everything above the line. So there's that one. And now we have one more equation. It's 2x plus y is less than 6. Let's get this guy into slope-intercept form. So y is less than or equal to a negative 2x plus 6. Graphing this one, it has a y-intercept of 6. 1, 2, 3, 4, 5, 6. And then it is a slope of a negative 2 over 1. Down 2 over 1. Down 1, 2 over 1. It's getting a little bit tricky to see here. Let me start over. Down 2 over 1. Down 2 over 1. Down 1, 2 over 1. Down 2 over 1. All right, connect these with a solid line. And now it says it is less than or equal to, so that means it's everything below the line. So it's going to be below the line all of this. Oh man! So our answer is a bounded region. A bounded region means that it's closed, where it is where the green, the red, and the blue come together. Come together right now over me. Anyway, this is our bounded region, this triangle right there. So make that extremely dark so I can see that, and there's no doubt in my mind that you have the correct answer here. Make that extremely dark so I can see it very, very clearly. All right, So if this is our bounded region, we've done this part. Once you have found the shaded area, that's what we just found. It's that black triangle up there. We want to find the vertices. So the vertices are the points of that triangle, the vertices of the polygon, as a reminder from geometry. So one of them is 0, 0. Hopefully you can see it. It's right at the origin. So I'm going to put that right here, 0, 0. Another vertice is this one right there. It's right 2 up and down 0. So it's 2, 0. And our third and final point is this one right here. It is right 1 up 4. Right 1 up 4. So those are our three vertices. 0, 0. Whoopsie, not 0, 0. This is at 1, isn't it? I apologize for that, class. So our first one is 1, 0. Then it's... Am I making mistakes all over the place here? What's our second point here? So, okay. Woofta! Let's see if I can make this more clear. This right here is our origin. Right there. Okay, so now it should be easier to see here. We're going to say that this point is 1, 0, which we have. This point is 3, 0. And our top point is right 1 up 4. Okay, now we should be good. So we have our vertices now, so we've done this part. And we want to find the maximum and the minimum for the values of 3x plus 2y. So when this goes right here, we want to find the highest number when we evaluate and the lowest number. That's what the maximum and the minimum means. So 3 times our x-coordinate, which on this case, our x-coordinate is 1. So 3 times 1 plus our y-coordinate of 0. So when we evaluate, 3 times 1 is 3. 3 plus 0 is 3. So we get 3. Our next one is 3 times x, which is 3 times 3, plus my y-coordinate, which is 0 again. So our next evaluation is 9. Last one in function notation, 3x plus y, we get 3 times x, which is 1, and 1 plus y, 1 plus 4, 3 times 1, which is 3, and 3 plus 4 is 7. So we get these three numbers on the right, and these are what we pay attention to for our maximum and our minimums. Our minimum value is the number 3. Here's our minimum. It lies at 1, 0. It's that ordered pair right there. Our... rats! I'm making mistakes all over the place! Our maximum value, stink. Here's our max. Oofta. Here's our max. Our max is 9. And our maximum value lies at 3, 0. Maximum is 9. It is at 3, 0. Our minimum is 3. And it is at 1, 0. Alright, you guys try the last one. Maybe you'll do better than I did, because I sure made a mess of this one. Pause the video, try number 4 on your own, graph all 3 of them, get a shaded region, find the vertices for that, evaluate it for 5x plus 4. Pause the video, try it on your own. Alright, we got a lot of work to do because we have to put these into y equals mx plus b form. So y is greater than or equal to a negative 2x plus 3. So a y-intercept of 1, 2, 3. A slope of down 2 over 1. Down 2 over 1. I like to put all of these points on here, class, because when I do get intersection points, it's easier to see a bounded region when we have these. So that's why I do all of these points. You wouldn't have to, but I think it's easier to see that way, personally. So there's our first one, and the shading is greater than or equal to, so it is everything above. Everything above is right here. There's our shading, and there's our first equation. Second equation I'll do in green. So we have adding an x to both sides, 3y is less than or equal to a positive x plus 9. Divide both sides by 3. Y is less than or equal to 1/3 x plus 3. A y-intercept of 3. 1, 2, 3. And then a slope of 1/3. Up 1 over 1, 2, 3. Up 1 over 3. So on and so forth. All right, connect these dots. And now our shading for this one is less than or equal to, so it's shading everything below the line. So far our solution is where the red and the green come together. And then the last one here is this blue one. Where do I have room to do that? We'll try it right here. So if I subtract 2x, I get y is less than or equal to a negative 2x plus 10. So I'm going to have a y-intercept of 10. There's 10. And my slope is down 2, right 1. So down 2, right 1, down 2, right 1, so on and so forth. Maybe you're seeing something right now, and that would be parallel lines. This one is less than or equal to, so that means that it is below the line right in here. All right, it definitely gets tricky to see. You got to think about where do all three of these graphs come together. Where the red, the green, and the blue all have in common is right here. That's tricky to see, isn't it? You got to be very, very careful with your shading and very, very clear to yourself about where the points are and where the shading is. So that is your bounded region. And actually it's not even bounded. The reason why is because these two lines are parallel, so they will never, ever, ever get any closer to each other. So you're not going to get a polygon on this one for a bounded region. You're going to have an open side here. And so how many vertices do we have? We have one. Let's see if I can make this more clear again. You have one vertice right here, and you have one vertice right here. And your origin is right there. So you're only going to have two vertices on this one because the figure is not closed. So what are those two vertices? It is left and right 0, up 3. So 0, 3. And our other vertice is at right 1, 2, 3, and up 1, 2, 3, 4. Does that sound right? 3, 4. Let me check in my notes to make sure I did this one correctly. 0, 3, and 3, 4. So those are your 2 points. You don't have a bounded region, so that's the only two we have. So now let's evaluate these 2 points. 5 multiplied by x, which is 0, plus 4 times the y-coordinate of 3. 5 times 0 is 0, plus 4 times 3 is 12. 0 plus 12 is 12. Last one, 5 times x, which is 3, plus 4 times y, which is 4. We get 15 plus 14, so we get the number, we get 15 plus 16, which the answer then is 31. So our maximum value is right here. Our maximum value is 31, and it is at 3, 4. Here's a little bit of a curveball for you. The minimum value, I'm sure a lot of you put this, which is good thinking. However, there is no minimum value because this shading continues to go down forever and ever and ever and ever and ever, and it does not stop. So there's actually no minimum value. The minimum value would be negative infinity, so we just put there isn't one. There is none. So that's the answer for problem number 4. You're going to have a worksheet on that when you come to class tomorrow. Please feel free to ask me any questions on the notes or on the worksheet when you come to class tomorrow.